the live chat, and then there's Fire content below it. Slides are in the Fire content channel. So please feel free to go ahead and grab those. Thank you to our sponsors. I think everybody knows all of those organizations. Wanted to send a shout out to Herman and Emily, who kind of helped pull all this together. I also wanted to send a congratulations out to Herman, who accepted a job offer to come work at Active Countermeasures. So Herman is going to be a cyber threat hunter once he comes on board. Yay, this should be fun. So yeah, I've had folks ask in the past, like, oh, hey, you should hire me. And it's like, hey, I don't know you. So, where do we do our hiring? We do a lot of hiring around the folks that we hang with and the folks that we know. Herman, for God, at least 2 or 3 years now, has been helping out with webcasts and answering questions in Discord. And, anybody who's been here for a while, knows him as someone who's kind of active in the community. So that to me is huge. So thank you, Herman, for accepting. It's going to be have an awful lot of fun to have you on board. And yeah, so let's kind of get into it from here. We're gonna have a couple of we're gonna have one little lab I want you to do. But all you need is a browser for that. So that'll make it pretty easy for everybody to go through and do. But I wanted to talk a little bit about IP addressing and subnetting because I've actually seen the conversation come up in Discord a couple of times, and some people are a little confused about it. It's actually not that hard. Um, we used to have what was referred to as classful routing. So what classful routing meant was we said, hey, here's the range of IP addresses we have, and we're going to take a block of them and call them class A, a block of them call them B, a block of them call them C. And, whether they're A, B, or C is going to designate how many IP addresses you get as part of that allocation. And this was like one of the worst ideas we've ever done while rolling out the internet, because we burned through those addresses really quickly. Um, I can remember a time when I had a company, I was getting onto the internet. I was talking with their ISP, and I said, yeah, I need 4 Class Cs worth of addresses because everybody was using legal addresses internally back then. So, hey, I need at least 4 Class Cs. And the guy on the other end of the phone goes, can I just give you a Class B? It'd be a lot easier. Oh, okay. If I have to take a Class B with 65,000 addresses, I guess I will. And that's not how it happens today, right? You're lucky to get a single IP address out of your ISP, and they're probably going to charge you extra for it. So we burn through them pretty quickly. So we kind of scrapped classful routing and replaced it with classless interdomain routing, or CIDR for short. So if you've seen CIDR, weren't sure what it meant, hey, that's what it meant. And we tend to kind of designate that as a 1 or 2 digit number that shows up after a backslash at the end of the IP address. What does that number mean? We'll get into that a little bit as we go through. But as far as like what addresses are out there, here's a quick list of what addresses have been kind of allocated for specific purposes. Anything not showing up on this list is a potential legal address that may or may not have been allocated to an organization yet. And if it has been allocated, it may or may not actually be in use. How are addresses allocated? Anna kind of manages those addresses. And what they do is they take blocks and kind of push them out to registrar authorities that are responsible for different regions within the world. And then it's those registrar authorities that actually kind of dole them out from there. So it's almost like a little pyramid scheme. It used to be the internet that did everything. So if you remember when domains are free, you're old. You're old like me. The internet used to run everything. So that's where you got your IP addresses if you're a large organization. That was where you got domain names from, and you didn't actually had to pay for them. It wasn't until I think it was late 80s or mid 80s or so when that actually kind of kicked up and it turned into a monetary type of thing. But if you ever want to know who has been allocated what addresses, I gave you a link for it here. Now, keep in mind, some of these are going to be ISPs, and um, it's been allocated to an ISP, but that ISP may have reallocated it to one of their customers. Let's see. Eric was saying, yes, and in their infinite wisdom, the powers that be took the entire 127 address base for a loopback address. Yeah, Eric, that one's always kind of bugged me too, right? Why do we need so many loopback addresses? Like, you could argue, well, maybe they want to use a different loopback for different applications for some weird reason. Yeah, okay, fine. So that's what? A class C? Like we could have 200, like 127.0.0 dot anything could be looped back, and that would cover that no problem. Why we needed so many, I have no idea. So yeah, so what IP addresses, I'm sure you know, it's a series of four groups of numbers separated by periods. Unless it's IPv6, in which case it tends to be written in hex and it tends to be separated by colons, but that'll be a different class. I'm going to kind of stick with just talking about IP version 4 today, just to kind of keep things easy. Um, we perceive the numbers in decimal, but when you look at how are they being saved, how are they being transmitted, it's all being done in binary. Binary is the underlying basis of all the communications that we do. So with binary, you have values of one or zero that are valid, and that's it. Sounds kind of limiting, but there's a really good reason we use binary, and I'll get into that a little bit later. Digital kind of makes things run smoothly. But yeah, everything's in binary. So we may see, decimal or ASCII, then, make it's human legible. We can kind of understand what the word flags means and stuff once we know how to go in and do decodes. So this is all legible to us, but what's actually going on in the background is binary. So a tool is looking at that binary and converting it into an alternate format, typically decimal or ASCII, that makes it a whole lot easier for us to go through and read. Now, why are we using binary, right? Because binary seems horribly inefficient if you think about it. So, for example, if I had an analog signal, I could say, oh, hey, at this amplitude, that's the letter A. This amplitude is B, this is C, this is D, this is E. Oh, hey, if it's a negative, that's a 1, that's a 2. I could do a single signal and convey a complete piece of information like a letter or a number, right? So why don't we use analog? It's a lot more efficient. Well, the problem with analog, if there's any type of electromagnetic noise, the error rate goes through the roof, right? Like there's not a lot of deviation in amplitude between what we said would be an A or a B. So if any noise gets introduced here, they may have tried to transmit an A, and what actually went through is a B. Well, the way we can do error correction, we can't correct that single entity, meaning that the fact that it was supposed to be an A, but it got interpreted as a B, we probably not going to be able to figure that out. What we'll probably end up doing is transmitting a block of information and then have a CRC check or have some sort of a hash check at the end of that to make sure all the data got transmitted in a valid format. But with noise this bad, where we have a very high likelihood of errors, which means we're going to be retransmitting things constantly. And oh, by the way, this error rate would also apply to the CRC or hash check we're doing, which means we could actually transmit the right data, but the hash got corrupted. So we still think we have corrupted data, so we're retransmitting anyway. With binary, I only have two possible values, right? 1 or 0. And I can use, 0 volts to be a 0 and 5 volts to be a 1, or I could use a half a volt to be a 0 and 12 volts to be a 1. I don't want to go too far down into the electrical engineering side of it, but because the strengths and weaknesses of doing both. But the concept is we only have two possible values, and there's enough of a spread between them that as electromagnetic noise gets implemented in, I can still figure out this is a 1. I can still figure out this is a 0. So that little bit of noise isn't going to really cause us any issues. So how well does binary do at eliminating noise? Well, here I've got a system that is 1 week shy of being running for 2 years. And if I look at how many errors have been detected on the network, the number is still 0. You know, this reliability, this is the thing that we will go looking for the most, because that, cuts out the retransmissions and all those other problems. With full duplex Ethernet today, unless there's a hardware problem, there's really no reason to have errors to worry about anymore. Yeah, you go back to the old days of Ethernet when we were using, thick net or thin net, and Ethernet was actually a shared medium and we had hubs and stuff like that. Yeah, you might see errors on occasion. But the way we kind of set our networks up now, seeing errors is actually pretty rare and usually involves some sort of a failure that's taking place. So the reason we rely on binary is because binary is just so reliable. Imagine looking at that on a Windows host. Yeah. So we're transmitting things in binary, but we don't work in binary, right? No one like was born and taught binary as their primary language, right? There's no that I'm aware of any geographical region in the world today where their native language is binary. So we're always converting it to something else. Typically, what we're converting to is ASCII or decimal. And what the binary gets converted to depends upon the RFCs or the requests for comments or the protocols that we've gone through and defined. And sometimes there might be more than one table used. So for example, it's binary going down the wire, but when a system reads in the IP header information or the TCP, UDP, ICMP, whatever header information, those actually get converted to decimal. But once you get past the headers and you get into the payload, it's still binary being transmitted, but you switch over and start using an ASCII table for that instead. So when you grab a packet off the wire, there's actually two different conversion tables being used in order to convert that information properly. And if you look at something with TCP dump, you actually kind of see this taking place. I mean, we see header information up here, but that's because it's using the decimal table for that. But when it does a raw dump of what was in that packet, it only uses the ASCII table. Well, that's why, there's IP address information up here. There's a time to live value. There is, all the things you would normally see as part of an IP and a TCP header. And yet this output looks like gibberish. And it looks like gibberish simply because it needs to be converted to decimal, but the software just applies an ASCII table against all the binary. And that's why we end up with stuff that looks kind of weird until we get to here, in which case now it's legible because now we're into the payload of the whole thing. So Bill was saying the 4500 is a common start packets. Absolutely it is. So the number 4 means this is an IP version 4 packet. 5 means it's the IP header is 20 bytes in size. And 0 means type of service, differentiated service, whatever they're calling it this week, has not been set inside of the packet. Most packets don't bother setting that because most devices on the internet just ignore those settings anyway. But yeah, this is all my IP header information. You could manually convert it to decimal and read it, but you can see here because just one table is being applied, some of the data you can read, some of the data you can't. So one of the misconceptions I see is why do IP addresses only go to 255? And I've seen some folks kind of imply that like, well, they only thought they needed 255 numbers or decimal numbers. And yes, but no. That's not really the whole story. The reason 255 is the biggest number is because this stuff is actually being communicated in binary. So we have ones and zeros to work with. Any individual character here is referred to as a bit. When I pull 8 of them together, that's a byte. So we're communicating, a byte's worth of information. Well, how big of a number can I express using a single byte? Well, the way we convert it to decimal is each one of these values doubles in its decimal equivalent. So for example, this is equivalent to a decimal version 1. This is 2, 4, 8. Hey, you can read the numbers down the bottom. You can see where I'm kind of going like with this. So when we convert from binary to decimal, it's a simple matter of looking at what bits are turned on, what is the decimal equivalent. Let's go through and add up all those numbers. And whatever that number adds up to, that's what that byte was transmitting for a value. Again, this is working with the decimal table. So if everything's turned off, 0. If I turn everything on, well, the biggest number I can express is 255. So that's why you never see an IP address that is, 500.478. Whatever, because 255 is as high as we could go with a single byte of information. So some nomenclature here. Single value is referred to as a bit. It can be a 1 or a 0. If I collect 8 of them together, that's a byte. If I'm talking about half of a byte, meaning only 4 bits, that's sometimes referred to as a nibble. Yeah, I know. Bit, yeah, byte, nibble, RR. Somebody had a good sense of humor there. The one I see confuses people a lot is, what is a 32-bit word? Now, 32-bit words can have, or a word can have a different definition depending upon the CPU architecture. There are some RISC-based systems that use something else to define what they call a word. The way I'm going to define it here is how we we define a word in relation to IP-based communications. So with IP-based communications, the context you'll hear is 32-bit word. What does that mean? Well, it means what it sounds like. A word is simply a collection of 32 bits. Well, I've got 8 bits to a byte. 32 divided by 8, that's 4. So a word is 32 bits or 4 bytes worth of information. When we were looking at the IP header up here, I was saying 5 means it was 20 bytes in size. And you may have looked at that and you're like, well, then why doesn't it just say 20? Right? That doesn't say 20, it says 5. How do I know that doesn't mean the header is only 5 bytes in size? Well, because what that number is expressing is the number of 32-bit words that are in place there. So if I go in and I take 5, and remember we said a 32-bit word is 4 bytes. 5 times 4, that's my 20. So that's what that's expressing there. That tends to be the place we use it most frequently, although you see it used in other places in the header on occasion as well. So my IP addresses, 4 bytes, like we said, separated by periods. It's different with IPv6. We'll come back. We'll cover that a little bit later. And that number, a portion of that number describes the network itself, but a portion of that number describes that unique host's address. And how do we figure out which is which, right? Like, how do we figure out what portion is network and what portion is host? This is where subnet masks come in. So the subnet mask, which follows that same convention, my subnet mask can be is 8 bits. That can be a 1 or a 0. Um, Anytime my bit is turned on, that's identifying that corresponding bit and the network and the system's IP address is part of the allocated network address. If it's a 0, that means it's part of that unique host address. So the way you read this is that all of the bits in this byte are describing the value for the network. So that number is 192. So 192 is part of the network address space. This is saying, hey, all of these bits are describing network. Well, that's 168, so that's part of the network address. This is saying all of these bits is part of network. Well, that's 0. So 192.168.0 is the network, and my unique host address on that network, since these are all set to 0, all these bits describe the unique host address only, which happens to be 10. Now, well, Chris, 255, 255, 255, 0. If it's 255, it's network. If it's 0, it's host. And that is a true statement. But it actually goes more granular than that, which I'm going to get into in just a minute, and that your options are not just 0 or 255. I have 8 bits in each of these bytes that could be triggered as a 0 and it could be triggered as a 1, which would make these values end up being something different. And we'll talk about that a little bit more as we get into it. So why do we care about binary? Because it matters once we start getting into subnetting. Once you realize it's binary and once you kind of realize how this is all being used, all of a sudden the subnet masking starts making a whole lot more sense, right? And when it's something like this, where it's on an even byte boundary, it's really easy to process. But what if my subnet mask is 255.255.255.128? What does that mean? Right? It's not a zero, it's not a 255, it's 128. What does that mean? Well, if I go back to the bits, that means that all of this is network plus this one bit and that last byte, because that's the 128 bit, right? 1, 2, 4, 8, 16, 32, 64, 128. So from here over is all network. That means I've only got 7 bits left to address any of the unique hosts that are on it. So that's where that's coming from. And HK was saying slash 25. Exactly right. We've got 8 plus 8 plus 8, that's 24, plus one more. That's 25 bits that are being used to describe the network. So in CIDR format, that would be a /25. So what do those CIDR numbers mean? Hey, there's a little peek for you. So yeah. So remember, we used to do classful routing and it was just horribly inefficient. So today we do CIDR. And with CIDR, we can get right down to the bit level as far as, allocating things, which gives us a lot more flexibility. And this can be, we could have 25 masking bits, which means I have fewer hosts but more networks to work with. I could have a /23, 23 networking bits, which means I have fewer networks, but I can have more hosts per network, right? As that number gets smaller, I end up with fewer networks and more hosts. As this number gets larger, I end up with more networks but fewer hosts per network. It's kind of that balancing act that you'll see go back and forth. 2 bits equals shaving a haircut. Slight, that's awesome. That is awesome, man. You know, is is all of the bits turned on a valid value? Yes, it is. It actually is, and it means that that address is the only thing there. So some examples of it being converted, right? So here we're falling on an 8-bit boundary. Those are easy. But then we get down into here, and all of a sudden we see, values that are not a 0 or a 255. And again, where these values are coming from is it's based upon which bits are triggered in what direction. So why subnet? Well, this gives you better control of everything. If you're not, when you're not comfortable with subnetting, you probably just go in and make everything a class C, which means you have 253 addresses you can work with to assign to hosts, and you just kind of call it done. Or 200, yeah, 253, 254, sorry, 254 host address to work with, and then just call it done. But sometimes that's kind of useless, right? Like if I've got a WAN environment where what I'm dealing with is I've got 2 routers talking to each other, well, that means I'm only going to have 2 addresses on that network, and there are 2 routers doing a point-to-point connection. So to make more IPs than 2 available is horribly inefficient. Now, if I assign a class C, well, that means I'm wasting most of the addressing in that class C that I could be using it someplace else. Why is subnetting more efficient use of the address space? Yep, completely agree. So here I just wanted to go through and kind of give you some examples to be able to look at. So, so here's the CIDR format. Here's what the last byte looks like, right? So assume 255.255.255 dot whatever this number is. And here's what that value would look like in binary. Here's the number of networks you get out of it. Here's the number of hosts. And as you can see, as we use up more bits for network, we get more networks out of it, but we get fewer hosts per network. Now, it's not, there is a loss here. The more networks we create, we're losing 2 addresses every time because we need one address to assign to the network and one address to assign to broadcast. So we're always going to lose 2. So for example, we said, hey, if I've got 2 routers talking point to point to each other, I only need 2 IP addresses. Well, technically I need 4. I need 4 addresses because I need one for network, one for host, and then 2 addresses, one for each of the 2 routers that are going to be communicating with each other. And if I carve them up into those small little chunks every single time, that allows me to go through, I'd use this here, /30. right? So I can get 64 networks instead of just one with two usable addresses on each, but I'm losing two addresses every time. Now, I'm only getting two per, but I've created 64 networks. If I do the math, that gives me, that means I've got 128 total addresses to work with instead of the 255 that we had up here. So there's some loss in order to be able to assign to the network and the broadcast address every single time. Now, there used to be a concept of supernetting. And supernetting was when you subnetted in a way that was larger than the class involved, right? So I might say, 192.168.1.10 / 23. And since 192.168 is, 192.168 is part of the class C addressing, I was actually, allocating, more addresses, 512 addresses on it, using that subnetting. That would be considered super netting. But I'm not sure this term really means anything anymore because we're using CIDR and it's classless routing. So we're kind of ignoring the fact that, hey, that particular address used to fall into the class A bucket or the class C bucket. There's no A, B, or C bucket anymore. We're kind of ignoring that. But you might hear that term, and usually what it just means is, we're making a larger network segment. This is the first time I've heard about super netting. Yeah, dude, that's just because you're not as old as me. Now, you may be, so for those of you who's done packet decoding before, you're probably thinking to yourself, wait a minute, Chris, you said the biggest number we can express with a byte is 255. That works out for IP addresses. That works out for things like the time to live, because the time to live can't ever be bigger than 255. But how am I identifying port numbers, right? Because port numbers can go all the way up to 65,535. How do we identify a port number bigger than 255? And the answer is we do it as a 16-bit value. So we just take 2 bytes and kind of string them together. And that allows us to identify numbers that are much larger in size. So you can see here, I've got 2 bytes, but I just kind of pretend it's all one single byte. And I keep going up, right? So with a single byte, my my most significant bit has a value of 128. So now I jump into that second byte and I say, okay, I'm going to start at 256 and keep doubling on my way up. So if I take all of these numbers and add them up, that's where that 65,535 comes from. So we have things like port numbers that'll go through and use this. That'll go through and use 2 bytes in order to be able to describe information. Now you have things like sequence numbers that use an odd number of bits, right? They don't use two full bytes. They only use a part of 1 byte to go through and describe numbers. Yeah, how big can that number go? Well, you do this with the number of bits that are available, and that'll kind of give you what that value is. Can we do weird masking? In other words, is this considered a valid mask? And the answer is technically, yeah, it is. Um, I used to refer to this as my law firm masking. Why did I call it my law firm masking? Because back in the days when I was consulting, so for anybody who's done consulting, you know that the hardest people to get to pay you is lawyers, especially the small offices where there's like just a couple of them and they think they're bigger than they really are. They would much rather go argue in court why they don't think they should pay you in full versus actually pay the damn bill that they agreed to in the first place. So if you do consulting for law, so if you get into consulting, don't be surprised if law firms are the ones you have the most trouble getting paid from. At least that's what it used to happen to me. And back in the day before we used CIDR format, you could actually do weird subnetting like this. Now, it was hard to work with because IP addresses weren't continuous, right? It wasn't like you could say, oh yeah, hey, I'll have DHCP hand out addresses between, dot 100 and dot 200 because everything in that range is a possibility on this network. No, no, no. It might be, oh yeah, there's that you can assign 3 and then you can assign 11. It's got a weird numbering scheme to it. But the reason I used to use that at law firms is because I knew they couldn't just plug a system in and have it work. They would have to come back to me and say, hey, we need an address for this. And I'd be able to say to them, sure, no problem. I will give you that information as soon as you are current on your billing. And that's how I got law firms to pay me. Now, with that said, I have gone through recently and kind of checked like Linux and Windows and a few other OSs to see, can you still get away with doing this? And you can't. So technically, could you have this? Technically, you could, but most operating systems don't support it, right? So there's the possibility, and there is the does the software support it? Those are two different things sometimes, and this is a good case of that. A couple of folks are saying, you know, good use case. Yeah, sometimes sometimes as a consultant, you need tricks like that to make sure you get paid. So again, everything's in binary. And how we perceive that binary or how our tools perceive that binary comes down to what tables are being used. This is where obfuscation comes in. Because what I may do is I may say, okay, it's expecting ASCII, but I'm going to use base 64 instead, or I'm going to use some other format. And what this does is the same information is still being conveyed. It's easily accessible if you know what table to use. It's almost like it's encrypted, but it's not because you don't have the overhead of encryption and you don't have keys to worry about any of that. But it does, it's not encryption, but it's what we refer to as obfuscation. And here's a good example of that, right? I might have an intrusion detection system or a data loss prevention system, or I have something that checks all the packets going by to see if the word PowerShell is there, right? I think, we all know PowerShell can be bad, right? PowerShell is great when we're the ones using it. PowerShell is friggin' scary when it's an outside malicious entity triggering PowerShell on our systems. So anytime PowerShell gets run, we want to know about that. There's the old saying, Marion Accounting doesn't use PowerShell. So if you see Marion Accounting's computer running PowerShell, that's going to be really bad. You're going to have a bad day. So, as an attacker, it behooves me to make sure it's hard for you to detect that I'm trying to run PowerShell. Well, most data loss prevention systems, intrusion detection systems, whether they be network based, whether you're running a proxy that's acting as an intercept proxy where it decrypts things and then checks the payloads and then sends it on from there, they're all based on pattern matching. So if they're looking for PowerShell, all I got to do is convert it to a different format like hex. And all of a sudden, it doesn't look like PowerShell anymore. This still says PowerShell. Go find a hex calculator online and convert that, and you will convert it to ASCII. You can't convert it to decimal. You'll end up with something different. But if you can take that string and convert it to ASCII, that just says PowerShell. So it's still there. Um, this, obfuscation like that is one of the best ways to kind of bypass a lot of these addresses. I'm reminded of a place I worked at where the management staff was a-holes and they didn't want anybody doing anything non-work related on their computer ever. And it wasn't like they were worried about viruses or anything. It was at a time where that wasn't really a big deal. It was more, they did not want you using your work computer to like visit a work site or something like that. And what me and a couple of buddies figured out was instead of typing in sports.com, if you converted it to hex and typed in the hex string, you got to sports.com because the system they had checking didn't see sports.com. It saw a hex string and it decided that was okay. So again, um, taking advantage of the fact that your systems understand these different tables. And if you send it in a format that it's clear to them that, you're using a different format outside of ASCII or decimal, They may just do automatic conversions for you. So yeah, so obfuscation is a great way to kind of hide your tracks. So let's play around with this a little bit and see how hard is it to actually obfuscate things. So what we're going to do, I will throw this into chat just in case you didn't download the slides yet. Copy the link. I'm going to throw this into the chat on Discord and just go ahead and click that link. Don't worry about it. It's fine. There's never a problem with anything here. So just go ahead and, click that and open it up. And that'll open a tab. And you should see something that kind of looks like this. Okay, let me kind of zoom in a little bit so you can see it in case you're too afraid. But you're going to see something like this. This is kind of interesting, right? Because look at that. It looks a little bit like gibberish, but it doesn't because you can clearly see there's some patterns taking place here, right? Yeah, Kafka was saying base 64. Yep. So clearly someone who's done this a lot, right? When you can look at something like this and say, yep, I know the table format right off the top of my head, you've been at this for a while. So there's some patterns here, right? And with real encryption, one of the goals of encryption is to hide any possible patterns, right? That's one of the things we always try to do with encryption is we want to make sure there's no obvious patterns. Or with good encryption anyway. We want to make sure there's no obvious patterns. So there's obvious patterns here. But, you know, what does this say or what image is this showing or whatever? We have no idea. We can't tell. So what I'm going to do is I'm going to zoom that back out a little bit. Yeah, that's a good one there. And then I'm going to go to the next slide because let me copy this. We're going to work around with CyberChef. Now, if you've never used CyberChef before, this is an awesome tool. CyberChef is just simply a conversion tool. So it converts between different formats. So for example, we were talking about base 64. I could take text and convert it to base 64. And notice it gives me a little example that says, e.g., hello becomes blah, 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 blah. That's one of the things I love about this tool. The context sensitive help is awesome. But if I already have something in base 64 format, it'll convert it back out for me. So this is a great little tool to go through and use to be able to convert stuff through. Now, if you don't want to use something that's online, you can run this command on a Linux system. Well, I actually might work on Windows too. I haven't tried it. I've only used this on Linux. And you can actually set up your own local CyberChef instance that's running. So what this command does is it leverages Docker. So you got to have Docker on your system. And it goes through and it pulls down an image for CyberChef. So if it's not on your system already, it'll automatically download it for you. And it maps port 8000 on the local system to port 8000 on this Docker container. And that's just CyberChef running. I will say I learned something new recently. See this restart always? So what the restart always command does is it says, hey, I want to start this container up. And if the system gets rebooted, I want it to automatically start back up again. What I didn't realize is that there's a timer in play here. The timer is, so they say it's 10 seconds. I think it might actually be longer. So here's what happens. So I go in and let's say I run this Docker command. Docker goes in and says, great, here's what I'm going to do. I'm going to wait a period of time. And then I'm going to check to see, is this image running in a container? In other words, did it appear to launch successfully? And if it did, great. I will make this command permanent. If it didn't launch successfully and I don't see it running, well, telling it to restart all the time might cause problems, right? If this container crashes for some reason when it tries to start up, well, now I'm going to get stuck in this loop where it tries to start, crashes, tries to start and crash. So this is an intelligent way to kind of get around that. So what all Docker's doing is it's saying, okay, I'm just going to wait a little while. and then I'll check. And if it's running, great. If it's not, oops, we won't kick that command in. Well, I had a VM I was setting up for a class I was doing. I ran this command. I went and checked. Yep, CyberChef is there. I can get to it. Awesome. Kill that container for now. Let's go off and do something else. And it was prior to it figuring out that, this should be done persistently. So if you have a Docker instance you're pulling down and you're going to use the restart always command, my recommendation is wait at least 30 seconds, 60 seconds if you want to be really sure before you shut down whatever computer it is that you're running this on, because otherwise this may not actually come back for you. So just a hint, just a hint from someone who got burned by that. All right. So here's what we're going to do. I want you to open the tab that has all this weird text on it, and I want you to hit Control A and then hit Control C. And that is going to copy all of this information for you. Then what we're going to do is we're going to come over to CyberChef. I'm going to click within this input window, and then I'm going to hit Control V. And I'm just going to paste all that stuff in. So again, if you're following along, all I did was copy all the text off of this tab, right? Control A, Control C, came over here, click in the input window, Control V. That's all I've done so far. So now here's CyberChef saying, hey, yep, here's the output from that. Now, see the little magic wand? The little magic wand is kind of like a hint. CyberChef tries to be intelligent, and it tries to figure out what format was actually pasted in up here. So if I mouse over this, it says, hey, that looks like base 64. And if I'm right and it is base 64, here's what your output's going to look like. So it'll give you a little preview of what you might say. So now what we're going to do is we're going to click on that magic wand, and notice that automatically created a recipe to convert what's up here from base 64 to create the text that we see down here. Now, still can't read this, right? But if we look at it, you'll notice a pattern. And the pattern is we have numbers and we have letters A through F. Well, numbers, letters A through F, that's hex, right? Pretty straightforward. So if I come over here on the left, now I have it under my favorites. You might need to go under data format and go looking for it in here someplace. So if you don't see it up under favorites, don't get freaked out about it. Use it once or twice, and then all of a sudden it becomes a favorite for you. But we have hex. The goal is always to get it to ASCII. So what I'm going to do is I'm going to say from hex. So I'm going to click on this, and I'm just going to drag it over to this middle window. So you can probably see a little faint from hex there. That's because I've clicked, dragged it over, and I haven't taken my finger off my mouse yet. Once I drop that, it'll automatically go through and do that conversion. And as soon as it does, you can see, oh, wait, now this is readable text down here, right? This looks like maybe it's like an email or it's a paper on something on the effectiveness of aluminum foil hats, an empirical study. Huh. Why would someone try and hide this information? Why would they not want this to be viewable if there's some sort of study that was done on wearing aluminum hats? Well, if you skip down the bottom, one of the things that they kind of get into is they say, well, we think that tinfoil hats will protect you from the government actually came from the government itself, because wearing a tinfoil hat doesn't protect electromagnetic signals from getting to your brain. It amplifies it. So the government pulled a switcheroo on us. Hey, wear this helmet. This will protect you from us. Oh no, it makes it easier for us to get into your brain. So maybe that's why somebody was hiding it. Maybe this is some sort of secret information. Who knows? It's a joke. This is a joke. I will say that right up front. This is a joke. But this study was actually done. This is like one of the cool things I love about being a geek is that there are those of us that will say, this is a complete waste of time, but it'll be funny. So I will invest time and resources into something I know is a waste of time for the simple purpose of doing something funny. IP over avian as an RFC is a great example of that. There are two RFCs. So RFCs are those requests for comment. Those are what become our standards for doing IP-based communications on the internet. The first one defined the protocol for IP over variant, avian. So basically what it is you have a message you want to send, you send it to a printer, you print it out, and then you tie it to the leg of a pigeon, and then the pigeon carries it some distance that, there's no internet, and then it gets received on the other side, and then you use an optical scanner to scan that data back into the network again, and you can send it off from there. Yeah, one of the avian carriers for QoS, yes. Yes, there is a spec around quality of service. There was actual testing done, and I think they experienced like 50% packet loss because there was hawks in the area or there was hunting season or something weird happened. Half the data went through, but no one had actually, someone created this IRC that was clearly a joke. Someone said, well, we need to test that. And they actually went out and tested it. Go figure. So they got a bunch of pigeons together and, hey, let's try and transfer something over. So yeah, people will put a lot of time into stuff like this, and that's actually what there was. These individuals were at MIT and did actually try to do as close to a real scientific study as possible as to what impact does it have when you wear a tinfoil hat. Does it protect your brain from radio frequency waves or not? And they do, and they basically figured out, yeah, no, no, it doesn't protect you. It actually makes it worse. And then they kind of got into, well, then who would have came up with this? Well, the only one with somebody to gain was the U.S. government, so it must have been them. And yeah, okay, time to put our tin. So you kind of have to put your tinfoil hat on to believe what you were reading about the study on tinfoil hats. That's really what I think it kind of comes down to. Cool. So we talked about this. Yep, control paste. And this is all on the slides. So if you can't do this right now for some reason, grab a copy of the slides. You can see I kind of walk you through the whole process. Note you can, if for some reason you don't want it to automatically process data, you can uncheck auto bake and that will stop happening. And now it won't bake until you hit the bake button. But yeah, why click things if you don't have to, right? Did the tinfoil hat thing twice green? Okay. So you get the idea. And like I said, this is more than enough to bypass most security checks. So we don't need, so like folks make a big deal about, don't use des encryption. It's, too easy to break keys and blah, blah, blah. And, well, context matters, use case matters. What are you trying to accomplish? If you what you're trying to accomplish is, hey, I'm going to take people's social security numbers and their home address and I'm going to save that to a disk drive. Yes, absolutely do not use des encryption. In fact, you should not only look at how hard is it to try all the possible keys in that encryption today, you want to look at what is the life value of that data, right? So if you're storing, social security numbers for people in their 20s, that bad data is probably going to have value for the next 60 years. So now the level of encryption you're using to protect that needs to be something that can stand up to brute force, not just today, but 60 years from now as well. So yeah, there are cases where very strong encryption makes a really good sense. But if I'm an attacker and the key for des key is public. Well, some des keys were published. There was a study that was done to see how long does it take to try all the different key combinations. So honestly, I think des gets a poor it gets slighted unnecessarily. Des encryption was written by this guy, Robert Morris Sr., who was an awesome dude. I'm sure Bill remembers him because Morris worked with us at Dartmouth. That was actually Dartmouth tried to hire me for their Institute of Security Technology Studies, and one of my requirements was that I get to work with Robert Morris Sr. Because he was just a really cool, smart dude. Um, but he's the one that, and if Robert Morris sounds familiar to you, it was probably because his son wrote the Morris worm. Uh, I think that was a kid trying to keep up with dad and didn't quite do it the right way. Although he's a good dude too. I got to meet him one time. But in any event, desencryption has actually held up pretty well. No one's found backdoors. No one has found problems with the algorithm itself. The problem with desencryption is that it natively supported a 56-bit key. And our processors run so fast today, it doesn't take you long to run through all the possible key combinations that would fit inside of a 56-bit key. And we did a couple of things like we came up with triple des where we used three keys combined to get around it. But the real replacement for that was AES. With AES, we can do 128, 256, 512. I think there's a 768 spec out there now. You get the idea. But sometimes, whoa, my bacon number for Morris is two. Okay. But like I said, sometimes strong encryption is required, but sometimes most of the time it's not. So if we're an attacker and our only goal is to get information through your perimeter that is potentially evil, and we just want to get it through your perimeter and not get it detected as evil, there's no reason to encrypt that. There's no reason to, make this any harder than it needs to be. Simply swap a couple of table conversions and bang, you're off to the races, as you can see. And tools to help, here's some conversion tables that might be helpful to you. I got an IP calculator link for you here. And I already gave you the link to CyberChef. I also gave you the command to be able to run it locally if you want to. Now, next week's Fireside Friday is going to be on packet sniffing tools. Yay, packet sniffing. So we've, covered a lot of the basics. I want to start getting into like, what can we use to go through and kind of start pulling packets apart. Um, so what you will need ahead of time if you want to do any of the labs next week, we're going to be working a little bit with Wireshark. We're going to be working a little bit more than that with T-Shark. And the data file we're going to use, I gave you a link for here. TCP dump is optional. I kind of show you TCP dump next week, but we don't do a whole lot with it. Really what I want to do is I think T-Shark doesn't get enough love, right? Wireshark has the GUI, it has the colors, it gets all the writs. That's what everybody pays attention to. But T-Shark is a really cool tool. And you can actually do things with T-Shark you can't do with Wireshark, even though they're based on the same code base. So yeah, so we're going to have another Fireside Friday next week, same time. And if you want to be able to do the labs, here's what you can go through to get yourself prepped for being able to go in and do the labs. And with that said, we are done. Oh, I do want to give another plug for the book club that had their first meeting today. So they had picked up a book the beginning of February, and then folks went through and read it. There was some commentary made, and then they had a final meeting to kind of talk it through today. So that was earlier this morning. But they're picking a new book for March, and the new book for March is Sandworm. So I'm sure someone will go in and post a link for that. But if you haven't read that book, you really should read that book. It's a really good kind of view on what goes on nation state level. What's out, what are we really kind of dealing with out there? It's a great read. And it's kind of cool to be able to read it while other people are reading it. So you can go through and kind of discuss some of the things you're finding. So there are Discord channels on this same Discord server that are there just to go through and kind of discuss these books. So I highly encourage folks to be able to jump in and kind of take advantage of that. With that said, I think we're done. Bill, Keith, you guys got anything? I'm going to go back on camera for a little bit.
No, actually, again, you're great at, getting all the comments and answer questions in Discord. So I think we're good.
Oh, Keith, you talk about me like someone who, decides whether you keep your job or get fired.
But yet I still speak the truth.
That's the way to do it.
Yeah.
Yeah. Yeah, and
Hey,
hey, another month. and maybe we can drag HK on screen with these things too. So
Ooh, there we go.
Hey, hey, he'll be on the other side.
yeah.
Man,
And I see a lot of thank yous. That goes both ways. There was a comment made before this even started about, this being free training. And, the way we look at this is not free training. You were spending your time. You could have chose to invest your time doing something different. You didn't. You chose listen to us talk about, IP, subnetting, obfuscating, and, toilet paper origami. So we do very much appreciate that. So the thanks goes both ways.
yeah, I
Yeah,
just want to
remember
second that.
today is purchase blackout day. Yeah, that's true, Bill. Thanks for calling that out.
Just grab it tomorrow. There you go. Good purchase for the start of March.
Yeah. So it's okay to steal it today, but if
Yes.
you're going to actually buy it, please wait till tomorrow. Yeah.
Oh, well done. Well done.
Uh,
awesome.
so
Well, thank you, Chris. And again, thank you all for attending and especially all the engagement on Discord. All the questions, answers, comments, they've all been great.
yeah.
We just have an awesome community here, and I appreciate that.
Oh, Kafkar was asking, not overly familiar with IPv6. Do the same rules with subnetting apply? Yes, it's a bigger value, right? IP6 addresses are much larger in order to accommodate the number of devices that we have out there today. But the way subnetting works the same way. We just tend to subnet things larger because we're not as worried about losing address space, at least not yet. But I haven't, and Bill, correct me if you've seen differently. I haven't actually seen like, 255.255 being used. It's always CIDR format.
Yeah, it always is because it's just too big. And there is no true broadcast address for IPv6. There's multicast,
Yep,
but
that's true.
a couple of quirks in there. I've got an IPv6 for IPv4 users. I'm going to see if I can find that presentation. I
Yeah,
can't
that would
remember.
actually be an awesome one to do as part of this series.
Yep, yep,
Yeah, because the other thing that's different is with IPv4, um, the next header after the IP header is always your transport header. It's always, TCP, UDP, ICMP, whatever the case happens to be. And with IPv6, you can actually have multiple headers. You can have your source routing header, and then you can have your endpoint header, and then you get your transport actually showing up after that. So that was one of the things they did to keep the header from being able to change size.
yep. As to whether we'll run out of IPv6 addresses, somebody actually went through and did the math. There are more IPv6 addresses than there are atoms on the surface of the Earth when you count land and water. So we're not going to run
So
out.
we've got at least 10 years.
Yes, 10 years. And then we'll be panicking the same way we did with IPv4.
I think the thing that bums me out about IPv6 was that, so I actually remember that it getting developed over the 90s. And there was a push to get it out in like the mid 90s because it was, hey, so it turns out this internet thing is popular. And and we thought it was just going to be a couple of universities, but it turns out everybody kind of wants to get in on this.
No
And we're
way.
going to go through IPv4 addresses quickly. We really should switch over to IPv6. And I remember it seemed like the commercial side wanted IPv6. The academic side was no, no, no. We haven't, finalized the specifications yet. Let's, wait and make it perfect first. And, that didn't happen until like the early 2000s. And of course, at that point, it was like, I'm not going to use it unless you make me.
And now most of our machines will try IPv6 first.
Yep.
That's turning out to be the default for a lot of connections. So if you're looking down at your network wire and can't figure out why these weird headers are showing up, your OS is choosing to
Yes.
by default.
Yeah, and I forget what channel that was in, Bill, but somebody was talking about that where they were saying, "Hey, I have IPv6 shut off, and I'm still seeing IPv6 packets. I don't know where it's coming from." It's like, yeah, everything's going to try that first.
Absolutely. Chris, so we did that internally as a Fireside Friday at one point, and that was one that I did to give you actually a break off of this. If you're interested, I'd be happy to do a reprise out in public.
Perfect.
Good deal.
Perfect. Yeah, let's we'll kind of sync up offline and we'll figure out, hey, here's where to go through and shove this in because I think I have enough content to get us through till like May. But I don't want to wait until May to let you talk about IPv6. So we'll pick a week and yeah, I'll go off and drink tequila or something and
There you go.
you can educate people. So I
There
can
we
go
go.
off, drink tequila and send weird t-shirts to Fire Serpent. So
And how would this be different from any other Tuesday?
exactly. I know. I know. I'm sure in her mind her immediate thought was, "Oh, you mean a Friday." Okay.
Okay. Hey, thanks, guys. We really enjoy doing this, and thank you for making the time for us.
Yeah. Thank you everybody. Have fun.
Hey, thanks, Chris. Thanks, everyone.